Okay, I think we can start this webinar now. So first of all, a warm welcome to everyone who joined. My name is Niels Verdijck, and I will be your host today. Apart from being your host, I'm also a customer support engineer at Diabatix. So that means if you have any questions or if you do a project with us, you'll for sure get in contact with me again. Okay, so in this first webinar, or seeing as this is the first webinar of the year, I would like to wish all of you a very late Happy New Year. I hope you all enjoyed the holiday seasons. For this first webinar, we'll look at the influence that material properties have on generative designs, or the design that will be returned by our generative design tool. And this is the first webinar in a series or in a mini-series of webinars, which is called the flexibility series. So I will see where changes in the input how changes in the input will influence the generative designs that will come out of it. Okay, but let's start with this first webinar. And for this webinar, I'll be using a conduction case. It's a case that you all should very much, or should be very dear to you, or should be very familiar, sorry. And to you all, we'll be using a frying pan for this webinar. Okay, so let's go to the platform itself. So this is what you see on your screen is the platform itself, so our platform ColdStream. As you can see, I'm using currently using the demo company account. If you have your own access to the platform, you'll have of course access to your own account. As you can see, we organize the platform by using projects. So projects are similar to folders, and this is really to keep all of your different cases organized. So let's create a new project for this webinar. It's by clicking the Add Project button in the top right corner. Give it a name. So webinar material flexibility. And a description is also required. So first webinar flexibility series. And then click Add Project to create your new project. If it's successfully created, you'll be immediately be redirected to the new project folder, where you can create your new cases, again by pressing the top right corner. And you'll need to give it a name. I advise you to give it a sensible name to keep your project folders organized. And let's say it's a copper core, that's the name. And the naming will become clear later in this webinar. Next, all cases are of some type of, or all cases have a type, which can either be a design or a simulation. If you specify your case type to be of type simulation, then you let the platform know you just want to do a CFD simulation, for instance, or a thermal simulation. If you specify the case to be of type design, then you let the platform know, okay, with this case, we want to do an optimization. So we want to let the platform know that we want a custom design, which is of course what we want for our case now. So let's press design and add our case. Okay, now the setup of the case can start. So again, press the top right corner to start the setup. And next we have to upload a geometry. So select the step file that you like and populate the case. So what happens now is that the platform will extract all of the regions and boundary patches that are available in that step file, and will also perform some background checks to make sure nothing is wrong with it. For instance, overlapping regions or partially overlapping boundary patches, for instance. That's all. Those are all of things that the platform is checking during the populated case process. Once the step file has been uploaded, you'll be able to play around with the geometry in the GUI. As you can see, it's a pretty good mock-up of a pan, if I do say so myself. And on our left hand, you see a regions tree, right? All of the entities are available to you. Let's start with the handle. So the handle is of type solid, of course. The name can be as is. Select a material. Let's use material which has a very low conductivity. We don't want to burn our hands when we take the pan off the stove. So let's select that one. We can include radiation if you want, but we'll ignore it for this one. We can include a heat source. If you specify a heat source here, then the value is spread out evenly over the entire region. But handles do not generate any heat, so let's keep that value at 0. And I see there is a surface patch missing for this region, so let's add a boundary and give it a name. One capital. Select the boundary patch. Let's use this one. And again, so now I'm uploading this boundary patch separately by just pressing the Add Boundary Patch button here. You can also add a subregion to any region, and that's something you can do by pressing the Add Subregion button here. So again, the platform is extracting the cat entity that's in that step file and is performing also some background checks to make sure there are no solid regions in there, because if you want to add a boundary, it needs to be exclusively a surface patch that's stored in that step file. Let's wait a little bit longer. And eventually it is uploaded. So let's continue with the case setup. So the reason why I uploaded a surface patch, so it's the circumference of the handle itself, is we want to allow heat to be evacuated through the handle itself. So we do that by specifying this surface patch to be of type external wall. And then we'll need to fill in some parameters. So let's say the heat transfer coefficient is 10 watts per square meter Kelvin, which is a very reasonable value for an external wall. And then we have to also specify the environmental temperature. So let's say that we're cooking in the kitchen of 25 degrees Celsius. So let's input that value. As you can see, I incremented the 25 degrees Celsius by 273.15 to get the value in Kelvin. All temperature inputs are required to be in Kelvin. Next, we have the option to include a thermal resistance. So thermal resistivity from the handle to the environment, but we don't want that, so we can leave those two fields empty. The following input values have to do with radiation, but as you know, we ignored radiation effects in the parent region, in the handle region. As you can see, this box is unticked, so we can ignore these last three input boxes as well. All right, as you can see, this when all the relevant information is filled in, green check marks appear next to the entity. So that means that all of the information, or there's no more information that is that needs to be inputted. Let's move on with our pan itself. So again, it is a solid, of course. Let's leave the name as is, and then we select a material. Let's say it's stainless steel. Let's use the first one that we see. Yes. Again, we will ignore any radiation effects, so we'll leave that box unticked. And we don't want any heat to be produced in this surface area, in this region, sorry. All right. Again, we have a few boundary patches. This is for the same reason as for the handle. We allow heat to be evacuated to the environment through the edges of the pan itself. So again, we'll specify an external wall, give it a better name, and fill in the relevant information again. So again, heat transfer coefficient of 10 meters per square 10 watts, sorry, per square meter Kelvin, and an environmental temperature of 25 degrees Celsius. And again, we don't include any thermal resistance layer, and we can ignore these values once more. Then we have our target area, which is where you put your meat or your vegetables or fish, whatever you want to fry in your pan. Again, heat is allowed to escape to the environment, so it's an external wall. Give it a better name, target surface, and use the same coefficients as before. All right. Lastly, we have our heat source, or the last surface patch, sorry, is our heat source, which is on the bottom. It's our stove. I hope it's clear. And this is our, as I said earlier, our heat source. So we have two options. We can either choose a fixed temperature wall, as the name implies. We fix the temperature at that surface patch. Excuse me. Or we can include we can specify the surface patch to be of type heated wall, meaning that our surface or some heat flux is coming through that surface patch. Let's use a fixed temperature wall. Give it a better name. It's a stove, or at least a representation of a stove. And let's fix the temperature at 200 degrees Celsius. Again, emissivity and absorptivity can be ignored because radiation is not taken into account. Okay, those are the most forthcoming entities that have been defined. Next, we have to define this subregion. So this subregion will be our design subregion. So let's immediately select our subregion type. This tells the platform where and where not it can place material or can add our new material. So let's do that. Manufacturing technique, say CNC milling, add manufacturing settings. Let's use this one. So with these manufacturing settings, we say there is an RF min of 2 millimeters, meaning that all the features will be at least 2 millimeters thick. A delta of 6 mm, so 6 millimeters, meaning that our CNC milling tool operates in, or has a depth, sorry, or operates over a depth of 6 millimeters. And the final input value for this manufacturing settings is the orientation, where 0, 1, 0 means the y-axis. For instance, 1, 0, 0 means the x-axis, and the z-axis translates to 0, 0, 1. But we specified to be of type to be in the y-axis, because as you can see, the yellow arrow is perpendicular to our frying pan design region. So meaning that the CNC milling tool operates perpendicular to the frying pan target surface. Okay, the last thing we need to fill in for this design region is what material can be added by the optimizer. And let's say we want a very conductive material, being copper, of course. So let's use this one, which is a very high conductivity. All right, as you can see, all green check marks, and you also saw that the submit button is available. For design region, the setup is not complete yet. We need to let the optimizer know what to optimize for. We don't have any targets yet. So let's do that. On the target surface, we want the temperature as uniform as possible. So let's impose that. We add a target, and we specify a temperature spread minimization. So we want the spread of the temperature to be minimized. And we want that spread to be minimized around 150 degrees Celsius. So again, it's an input in Kelvin, not in degrees Celsius. Okay, of course, because we have a very high conductive material that will be added, it's best to specify a volumetric constraint as well. So again, we add a target now for the design subregion. And let's use the maximum relative volume constraint. And let's put it to 0.2, meaning that at most 20% of the volume of the design subregion can be filled with copper. Otherwise, the solution will be very trivial, meaning all of it will be filled with copper. It's more conductive than our steel. Okay, I think that's everything for the case setup. So let me quickly check my notes. Yes. All right. So we're ready to submit our case. So when you submit your case, the case is already uploaded to the platform, and some background checks are again performed. So, for instance, if there is something missing, or if there are some errors or warnings, a pop-up window will appear explaining all of the errors and warnings that are there, so you can preemptively correct those mistakes. Luckily for our case, we don't have any mistakes, so the submit your case pop-up window appears. And to finalize the submit process, we have to make two choices. And the first choice is to decide how many credits we want to spend or we want to assign to this case. And you can change that by dragging this slider around. So let's say 100 credits. So the amount of credits translates to how fast the case will complete. So more credits means that more computational resources are made available for you. This translates to the case being completed faster. The next decision we have to make is what resolution level to select. And we can either select a detailed design or a conceptual design. A detailed design, as the name implies, means that the results of the optimization will be very detailed, so very accurate, but it will take quite a lot of time, or it will take some time to complete. For instance, using 100 credits, for this case in particular, the platform estimates 8 days and 14 hours, there and thereabouts. On conceptual level, on the other hand, this time estimation decreases. So for this particular case, with 100 credits, if you use a conceptual level, the platform estimates only 7 days and 10 hours. So the conceptual level, resolution level is it's not as detailed as a detailed design, of course, and also the manufacturing constraints don't need to be met. So that's something the optimization process cuts back on, and that's why we have a smaller computational time. But let's use detailed design, and voila. Now the case setup is sent to the platform and the optimizer takes over. Of course, we don't want to wait for 8 days and 14 hours, if I remember correctly. So that's why I prepared for this webinar, of course, so I can stop the optimization process by clicking the stop calculate button and confirm that I want to stop this case. So when I do that, when you want to do that, all of the progress, all of the data is deleted. So meaning that if you, for instance, stop your case and resubmit it, hoping that it will pick off from where you left off, that will not happen. So really all of the data, all of the progress is deleted. So be careful when you click that button. Don't make the decision lightly. Okay, so this is our first case. Of course, the goal of this webinar is to show you how the material properties influence the generative design. So let's create a few other cases to compare this one to. I will not go through the entire case setup once more, so I will use a quick, very easy tool. Sorry, and the duplicate button. So if you press the duplicate button, you'll create a new case. Let's call it graphite corner. So once you press the duplicate button, all of the information is copied to your new case. So let me show that to you. So as you can see, we are in our new case because we are in the graphite core case now. And you can see that the geometry is directly copied from the other one, as well as all of the boundary conditions. So again, we have our stainless steel pan, we have our external walls through which the heat is evacuated to the environment. So everything is copied. So we just have to make the simple modifications to our case. As you can imagine from our from the naming of this case, we don't want to use copper anymore. So let's delete that one and select a new material, graphite. Yes. So as you can see, graphite has a conductivity more than 3 times lower compared to the copper from earlier. So this really allows us to check or to more accurately compare or to see the influence of the material properties. So select that one. And once that is done, that's the only modification we need to do. We can again submit it. So let's say, well, first of all, our validation process needs to complete, of course, and then we can simply click submit again for our case to be handled to the platform. All right, again, I'll stop it, of course, confirm, and I'll do the case setup once more. So we have 3 designs we can compare. We have 3 designs we can compare to each other. And let's, for this one, use a material which is right in the middle of graphite and copper, which is, as you know, saw from the name, aluminum. It's about 200, it has a conductivity, thermal conductivity of about 200 watts per meter Kelvin. Compare that to our 95 from graphite and 340 nearly of copper. Okay, and once more, our case is ready to be submitted. Yeah, that's everything I needed to explain about the case. So I'll close this section, or I'll conclude this section of the webinar by going through the 5 steps that were used during this during the case setup itself. So first of all, we uploaded the geometry, which is our steel pan and our handle, and all of the relevant subregions and boundary patches. You saw me do it in one go, except for the last surface patch. If you want, you can upload all of these entities individually and basically add subregions and boundary patches or add new regions individually, sequentially. But it's easier to do it in one big go, in my opinion, at least. Our second step in the case setup process is filling in all of the relevant boundary conditions. So filling in what type of material it is, what type all of those regions are. So for conduction case, it's all solids. Fill in all the properties of the surface patches, all of the external walls. Our third step was to specify or to fill in the information of the design subregion. So where we specify what material will be added by the optimizer. In a fourth step, we specify what manufacturing settings will be used. So CNC milling, it's these particular CNC manufacturing settings that we predefined. And our last step is to add all of our targets, which are indicated by this symbol here. If you hover over it, you can see how many targets are set on each individual entity. So for our design subregion, it was a maximum relative volume constraint of 20%. And we had an objective of a temperature spread and minimization around 150 degrees Celsius. Okay, this is all for the case setup, so we can move on to the post-processing. So we pass by the entire optimization process. Okay, I also performed an empty control, so meaning that I just performed expand it all first. Just performed an optimization where there's no, or sorry, just a simulation. It's of type simulation. It's a case of type simulation, and where there's no design region, so it's all filled with our stainless steel. And if we have a look at the target surface area, so let's, sorry, let's hide everything else and plot the temperature. We can see that there's a real big spread from around nearly 200 degrees in the center to more than 100 degrees lower around the edges. So that's why the temperature spread minimization objective was imposed. So let's look at our graphite core. So expand it all, and perhaps first look at what our design actually looks like. Make it a bit more visible. So as you can see, we see very thick branches starting not in the center, but somewhere in the middle. Perhaps I can show our target surface patch as well as a reference. So let's put it like this. So we're looking underneath from the underside of our pen, and we can see that all of these branches, all these thick branches, start somewhere, say, 1/3 out of the center, and are redirecting the heat outwards, which makes sense, seeing what we saw from the empty control. So if we now plot the temperatures as well, we can see that again we have our very high temperatures in the middle, which makes sense because the material here is very similar. But we see now that the temperature at the edges is very much higher. It's 20 degrees or so higher compared to our empty control. So meaning that our graphite branches, our graphite arms, are really pulling the heat coming from the center, because remember our stove is really centered here, and it's pulling that heat away from the center towards the edges, which is what we like to see. If you now have a look at our aluminum case, no, that's not the aluminum case, that's the case itself. If we have a look at our aluminum case, I will expand it all again. Or the handle doesn't really matter. And just show you the design once more. Again, I'll show it in green and put our target patch again. Yes. So what we can see here for the aluminum core, the branches are much narrower, and with our volume constraint, that means that the branches can go further or can have a longer radial direction, which makes sense, of course, because again, our hot core doesn't need any cooling, and so it really tries to pull away that heat to the outside. And because it's more conductive than our graphite, it doesn't need as thick branches compared to the graphite itself. And again, we can see that the temperature, the bottom temperature of our target surface has increased once more. So we started from around 96 with our empty control. We moved to 117 with our graphite core, with our graphite arms. And when we use aluminum, so with our longer but more narrow aluminum branches, we increased from 117 to 125 degrees. Okay, let's go to the copper core. So as you remember, this is the core. This is the material with the highest conductivity. So looking at the trend, we would expect to see even longer and even narrower branches, and this is exactly what we see happening here. We visualize that as well. As you can see, the start place of the branches is pretty much similar to our graphite and aluminum core. So just outside this very hot region. But the branches are even more narrow and even longer, so they spread almost entirely to the outside border, because the copper is more conductive, and of course, by using the maximum volume constraint, it allows the branches to be even longer. And that is also what we see happening here. Our minimal temperature, so our temperature at the edge here, has increased 13 degrees, if I remember correctly. So a quick recap. Starting from our empty design, we have a very high temperature in the middle and a very low temperature on the outside. So more than 100 degrees Celsius difference. If we add graphite, our least conductive material, or at least our least conductive material, all the cores that we used, we see that our minimum temperature at the edges increased, because the graphite is able to conduct the heat from the center more towards the outside due to the temperature spread minimization objective. But it cannot reach all the way to the end, because it needs very thick branches to conduct as much heat away from the center as possible. If you look at our more conductive material, our aluminum, we see that the branches are narrower and longer, but they start around the same place. And the same holds for our copper case. So the branches start at the same location, but reach out further outwards, making the temperature at the edges even higher. So overall, we increased more than 40 degrees compared to our empty control case, and we increased 20 degrees compared to graphite, or worst conducting core. All right, this is all post-processing I wanted to show. If there are any questions, feel free to leave them in the chat now, and I will cover them immediately during our Q&A session, which will start now. So our first question is coming from Hannah, who asks, what is type general? Okay, I think I understand your question. So during the case setup itself, you saw that our design region, or I specified at least our design region to be of type design. There is also an option called general. As you remember from my explanation, our pan can have a volumetric heat source. So this is by, for instance, inputting 500 watts here. So meaning that these 500 watts are equally distributed over the entire volumetric region, so of the entire CAD entity, everything that's highlighted here in perhaps everything in this darkish green. So those 500 watts will be equally distributed over that. Of course, if you want a more localized heat production, you can do that. You can do that by using a general or a subregion of type general. So, for instance, we don't want our 500 watts to be produced everywhere in this pan. We just want it very localized in this brownish region, and that's when you use this, for instance. So now the 500 watts is only generated in this this brownish region. Does that answer your question? I do hope so. If not, feel free to elaborate on your question in the comment section. Our next question comes from Sophie, who asks, why use a conceptual design? Yeah. So I explained when you submit your case, this is one of the checks. So yeah, really showing to you that our checking mechanism works. Of course, for a design, there needs to be a subregion of type design. So I will quickly add these settings once more to complete the case. Let's use the correct material. Yes. All right. So if you if all of the errors are taken care of, I explained to you that there are two resolution levels. That I think it's not really clear why you want to use a conceptual if a detailed design is available. So the first reason is of course timing. So let me slide this around. The detailed design will always take longer because it's more accurate and the manufacturing constraints need to be fulfilled. While for conceptual, it's less accurate and not all manufacturing constraints need to be fulfilled. But it's a very useful tool if you, for instance, start with optimization. So because it takes less time, it's easier to immediately get feedback on what you can expect from your design case. For instance, you want to mix and match different objectives, but you don't really know if they will work. Then a conceptual design is something that's really helpful for you. So you don't have to wait as long compared to a detailed case. So really, it's to fine tune your design setup. So it's a very powerful tool, in my opinion, or at least a powerful time-saving tool. So that's why a conceptual refinement level is available for you. I hope I answered your question as well. If not, feel free to elaborate on your question in the comment section. If I quickly look at time, I notice that we're running out of time. So I suggest that we stop our webinar here. Don't worry though, if you've put any other questions, I'll reach out to you via email. So don't worry, those will be answered. So the last thing that I need to add is or for you to try it yourself on our account or on our website. Sorry, you'll be able to get a trial version or get in contact with one of my colleagues to get a trial version. You can play around with our generative design tool yourself. Of course, most likely you won't use a frying pan, but more complex. For instance, in space, I can see conduction case very much likely, or in a lamp, for instance, where the space is very tight. I can see that, or I can imagine that conduction cases are very interesting to you. Of course, our generative design platform allows for much more fluid flow, forced convection, natural convection as well. So really, I advise you, I encourage you to get in contact with one of my colleagues and really try it out for yourself. We update our platform regularly. In fact, our new release was recently, our latest release was recently available or made available to the public, where you can, for instance, our updated support page. What else can you use? You can add comparisons. You can add comparisons of designs, for instance. So let's say you want to compare this one, our empty control, and our copper design. So add comparison. Really make it easy to have compare different cases with one another. So for instance, here we can see everything with the aluminum core. Here we can see everything with the empty control, so only the steel pan, and you can see everything with the copper core from all temperatures. Of course, no pressures and heat and mass flow rates. And you can see powers that were added. So for instance, only 5 watts was added in the empty control, but with our more conductive material, there's more heat that entered through the fixed temperature wall, and with the highest conductive material, even more heat was entered. Of course, so it's really useful to mix and match, or to compare, sorry, the different cases that you have. All right, that's all from me for today. I wish you all a very pleasant day or night, whatever your time zone, whatever the time zone may be. And I hope to see you for the next webinar or one of the next webinars. See you later. Bye.